Did the rest really good?
Get the view station set up.
Okay.
It will be right here, Monday at 6 o'clock. The exam will be a week from today in class, 9 to 10. And there's a month for Friday. And it'll be pretty elementary. It's just about the concept of numbers. There might be some surprising things. Okay, any questions before we start? Yes,
How long will the review session run?
get out last. Okay. My guess is, based on experience, hour and a half, somewhere between an hour and 2 hours. Something like that. Okay. This is kind of, I think, a warm-up section. We're going to get into stuff that's a little bit more into the under the hood and into the engine a little bit more. This is kind of a preliminary look at a concept called subspaces. Rn, you might have heard me slip the word a couple of times. Rn is a space, although I haven't really told you what that means. I'm going to tell you what it means to be a subspace of Rn. And then we're going to look at some important examples and look at some computations. So this is the beginning of kind of a theoretical framework, which is needed quite a bit for applications. For example, from something as simple as solving the matrix equation AX equal B, this provides a good framework. But when you get into things like differential equations, Fourier series, writing functions in terms of eigenfunction expansions, this stuff is very, very important. So let's kind of start with basic. What is a subspace? Well, sub usually means it's inside something, like a subway or something like that. It's under something, inside something. A subspace in this case, Rn is the space, and we're going to define a subspace as follows. Definition. A subspace S in Rn is a set or a collection of vectors satisfying following. Okay, so I'm going to write down 3 rules that any good subspace has to follow. The first rule is the 0 vector is in S. Your subspace always has to contain 0 vector. 2, if U and V are in S, so is U plus. Okay, that's another important thing. If you have 2 vectors in the subspace, when you add them up, they still have to be in that collection. Finally, 3, if U is in S and lambda is in R, so U is a vector that happens to live in this subspace, and lambda is a number, then lambda U is also 3 rules. That's it. 0 has to live in there. If you have 2 vectors, its sum has to be in there. If you have a vector and a number, when you scale that vector, it's still got to be in. I can think of 2 subspaces of Rn right off the bat. Do you got anybody give me one? I'm waiting for somebody to give me the smart aleck answer.
0.
0 is a subspace by its own little naked self, right? Because that rule would certainly be satisfied, right? And the only vector in there is 0. So U and V both have to be 0. What's 0 plus 0? 0. So it satisfies that. And what happens if you take the 0 vector and you multiply by a number? What do you get? 0 vector. So in a very silly way, Zero is a subspace of Rn. How about the other extreme? Rn, the whole shebang is a subspace, right? Because zero vectors in Rn, right? If you add two vectors in Rn, still in Rn. And if you multiply a number times vector in Rn, it's still in Rn, right? So there are two extreme examples of subspace, the whole thing and the zero vector itself. Of course, there are lots more interesting in general. Let me properties. Two and three are called closure properties. The property two says, okay, we've got to be closed under addition. Add two vectors in the subspace, it's still got to live in the subspace. The third property is called closure under scalar multiplication. Got a vector multiplied by a scalar or a number, it still has to be in the subspace. We can also collapse our definition to S is a subspace if one, S is not empty, and two, if, well, let me make this over here. One, S not empty. And two, if U and V are in S and so actually you only need one rule, basically this right here. By the way, does anybody know what I mean by not empty? Okay. There's at least one vector in it. Right, the empty set is a set that has nothing in it. So to be a subspace, it can't be just nothing. It's got to have at least one vector in it. And if you have two vectors and a number, then the vector plus number times other is still in there. Why is this the same? Certainly, let me point out that if you have these three properties, you have these, because zero is an S means it's not empty, correct? And if U and V are in there, then lambda V is in there, right? And U's in there, so U plus lambda V. So if you have these three properties, you have this two. Why are these two properties good enough? Well, first of all, I know that there's at least one vector in there, right? Say that X vector is in there, right? That means that the zero vector is in there, right? Because right. Oh, actually, what I guess say. Yeah, so let me do this. Things that there's any linear combination. Notice if you're not empty, there's some X vector in there, right? And so by this property, just take X and X to be the same and let lambda 1 and lambda 2 be 0, and you've got the zero vectors in there. Basically, just multiplying by that. Number two, if you have this property, just take lambda 1 and lambda 2 to both be 1, and you've got U plus V in there. And if you have this property, just take lambda 1 to be 1 and lambda 2 to be 0. and you have this. Right? So you can sort of think of it this way. This sort of mixes the scalar multiplication and the addition together all in one neat little package. But that's not too. Let me give you some examples. Subspace. R3. Let me give you one that's not the whole thing and not just zero. Okay, let me look at all vectors where the first two coordinates can be anything I want, but I demand that the third coordinate is zero, right? Is this all of R3?
No.
Well, can you give me something that's missing?
That's, yeah.
Okay, like no way is 0, 0, 1 in this,
Oh.
right? You okay with that? Okay, let's go through it. Is the zero vector in here?
Yes.
Yeah, just make X and Y be zero, so you're good to go on that. If you add two vectors, you'll be still there. Well, let's see what happens here. If I have two vectors and I add them up, these two vectors in the subspace must look like this. What is the defining characteristic of being in this subspace? It's got zero for a third coordinate, still does. Everybody agree with that? And what happens if you multiply a number times a vector in here? You get still a vector whose final coordinate is zero. Okay, so this is an example of subspace. Yes.
Could you just stop once you prove that the zero vector is in there?
No, because just because you know the zero vectors in there doesn't mean. So, for example, consider subset. Consider all vectors where basically what happens is when you add the x coordinate and the y coordinate, you get one, right? So, for example, 1/2, 1/2, 1, 0, 0, 1, and things like this. -1, 2, right? Now, can you like describe what this looks like? If I were to draw a picture, geometrically, try to represent.
Sure.
Yeah.
It's the XY plane.
No, it's less than that. It's actually contained in the
sorry.
xy plane. It's this line, isn't it? Now, unfortunately, this is not a subset. But here, I'm going to deal with your question here. Is the zero vector in here? Well, the zero vector is 0, 0. And do they add up to 1? No. So this isn't a subspace because it's missing the zero vector, right? So let's throw in the zero vector. So that adds this point here, right? Now is it a vector space? No, because here's the problem. Now it's got the zero vector in it because I just put it there, right? I just threw that into the line. But it's still not a vector space because, or it's still not a subspace because, for example, that's in your subspace. And so is that because the coordinates add up to 1. What happens when you add these up? The cornerstone out of one and equal. And again, you can see this geometrically. What I did in that computation there was I took this vector here and that vector here, I added them up. And now the vector is off the line and it's not zero vector, so it's not in. So yeah, you gotta make sure. Yeah, and in fact, the vectors don't scale right either. Right, because for example, multiply this vector, which is on the line, times 25, it shoots up like Jack and the Beanstalk, and it ain't on the line, right? By the way, going back to this one right here, what do you suppose this one looks like? This is a subspace. That's right. It does. I mean, if you think of any of you had Calc 3, and if you haven't seen this. Basically, this is like if the XY plane was the floor and the Z axis comes straight out, this would just be the floor. Right? Because the height off the floor is 0. That's essentially. And there are other spaces too. So let me give you this little exercise here. Set of vectors that look like this. X, 0, 2x, minus x is a subspace. R. By the way, it's clear, isn't it, that the 0 vectors in there? All you gotta do is pick x equals 0, right? So 0 vectors there. Let's see if you can verify that when you add two things, it's still that form. And when you multiply that by a constant, it's still
I have a question as well.
Sure.
So with that, R3 example, you said that the subspace was equal to R2, would that be incorrect?
That would technically be incorrect. It's like R2. They're isomorphic. We'll talk about this later. I mean, because actually what it is since you're using 3 coordinates, it's a subset of R3. It is the same as R2 in a certain sense, but it's not really by definition R2.
It's like geometrically the same, but you have to have that third coordinate in that.
That's right. R2 by definition is just vectors with 2 coordinates, all possible vectors. That's a technical point, but it's a good point. Any questions? Okay, here's another great source of subspaces. In fact, here is Jim's little Betty Crocker recipe, how to make your own subspace, right? Given a set of vectors. Let's say, I don't know, P1, P2, up to K in Rn. And I don't care what K is, you can pick any number of vectors, but pick at least one. Then span of P1, P2, P3. You know, substance. So this is a great way to, like I said, build your own subspace. Take any collection of vectors you want and look at all possible linear combinations, the span. Now, maybe it's not clear why this is a subspace, so let's kind of verify that. What does a typical element of the span, this is a good kind of review, if the vector x is in span of P1 up to K, then x, what does it mean for x to live there? Yeah.
X is a linear combination.
That's right. So I can find numbers, these what we called them weights earlier, I guess. Right. That's what it means to live in there. It's any possible linear combination of those K vectors. right? Now, I claim that this animal is a subspace of Rn. Certainly, each one of these vectors that I can write like this is in Rn because they're all linear combinations of vectors in Rn. Is the zero vector there?
Yep.
How can I build the zero vector out of these?
Set all the constants to zero.
That's right. One way that I can do it, there may be more than one, but one way I can do it is set all the constants equal to zero. If each Ci equals zero, then X is the zero vector. So the zero vector is in span of V1. Okay, if I add two things in the span, is it still in the span? Well, let's see, shall we? Let U and V be in span V1, VK. Then one, if you look at U plus V, this is equal to C1 V1 plus CK VK. This 2 plus D1 V1 plus DK VK. And this one is, and I added it this way because it's convenient for me to kind of look how to add this up. This should equal to C1 plus D1 V1, C2 plus D2 D2, up to CK plus DK. So the sum is still in there because again, it's a linear combination of D1 up to DK. Everybody agree with it? And notice also too, lambda U is lambda times C1 V1 plus CK VK. What can I do with that number? I can just multiply it through. This is lambda C1 V1 plus lambda C2 V2 plus lambda CK VK. So when I multiply it by a number, still in there, it's still a linear combination. And when I add it up, it's still in. Everybody okay? So subspace. How about that? This is probably a central example. So let me give you a couple of, so here's a couple of examples of spaces. Now that we're going to use this result here that the span is always a subspace. Let A be R n by, so it's an n by n matrix. So here we're going to go back to matrices. Now, let me remind you, this means that A has m rows and n columns, right? The column space of A anybody remember what the column space is? This span of the columns. So it's everything that's the linear, it's everything that's a linear combination of the columns of A, right? That's what the span, well, that's what the column space of A is a subspace of, so the column space is every linear combination. It's the span of the columns, right? And we already know that the span of any collection of vectors is a subspace. So the column space, since it's a span of columns, must be a subspace of Rm. Because ask yourself this, how tall are the columns? There's M rows, so the columns are all M high. So this is a subspace of R M. Right? And here's one you have not seen. This is called the null space of A is equal to is the set of solutions to homogeneous equation. A X. This is called the null space, and as you might guess from the name, it is a subspace of what should that be a subspace of?
Just this year, but
Well, one of the things that I'm glad you pointed that out. One solution to the homogeneous equation is x equals 0, right? So that's at least some good evidence we're on the right track, right? Because a subspace has to contain a 0 vector. But this is A is n by m. What's the size of x then? It must be n by 1. That vector x has to be n by 1 to multiply. So this is actually a subspace R n. So let me give you the following theorem. Let A be an R n by n. The column space of A, which is the span of the columns, is a subspace. And two, the null space of A is a subspace. I'm gonna actually prove this to you. It's important. Number one, call A is span column. And each column are so it is a subspace. Because we've shown the span of any collection of vectors is a subspace of wherever they lie. Everybody, that cool? The null space requires a little bit more work. And by the way, when I'm done with this, I'm going to show you how to figure out what they are. And these are all computations, which is good. So there won't be too much news here. Zero vectors in the null space of A because A times a zero vector is zero vector. So I've got that. All right. As you pointed out earlier, that's already. What else we got to do? We got to show that if you have two vectors in the null space, when you add them up, they're in the null space, right? So let U be in the null space of A. What does that mean? What does it mean for you to be in the null space of A? A must be 0. That's what it means. It means that A kills you. And AB is 0 too. Add these two equations up, and what do you get? In fact, I can pull that A out. So U plus V is in the null space there. How about that? Notice it's very important that it's the homogeneous equation. Because if what was on the right side is not zero, this would not add up to the same thing. Finally, suppose U is in the null space of A, and lambda is just any number. This means that A U equals 0. So lambda because after all, if I multiply both sides by lambda, I still get the 0 vector. And this is A lambda U is equal to 0. So lambda U is in the null space there. So there we go. It's a subspace. It's got 0 in it. When you add two things there, still in there. And when you multiply anything in there by a number, still in. Okay, so column space and null space is going to come up as a recurring theme over and over. So I'm going to show you now, I'm going to get practical, and I'm going to show you how to compute this. Okay, so let me start with this matrix here. Yeah. Let me give you a bit of argument. And I'm going to sort of justify this as we go along here. The pivot columns of A, whatever they are, if you can identify the pivot columns in matrix A, and you pull them out, that will actually be a basis for column A. And I'm going to tell you what a basis is really quick before we do this. Has anybody ever heard that word, basis? Well, what do you have to have in vector space? When we look at the column space, what is that? That's the span of the columns in the matrix, right? So it's every linear combination. A basis for a subspace A or subspace S is a set of vectors that is one linearly independent. Two spans S. Let me give you kind of a quick example of this. but as anybody think the basis of that? Remember this example where we had the three-dimensional vectors, but we always have zero in the third. I could, yes.
1, 0, 0, 0.
What one basis might be this. That's kind of the easiest basis, I think. Does this set of two vectors span this? Yes. X times this plus Y times this. Anything. Right. Is it linearly independent? Well, yeah, think about that. That's a great example, because put this in a 3x2 matrix, every column's a pivot column. Right? Do you think of another basis? There are usually many bases. This one's a little bit less obvious. You have to have x plus y, well, a plus b equals x, a minus b equals y, but you can always solve those equations. This is a linearly independent set that spans. So a basis in a certain sense is most efficient, because what it means is it's sort of the smallest spanning set that has no redundancies. Is this a basis? This spans, doesn't it? It certainly spans. Because these two span, right? That's a null. But it's not linearly independent, right? Because if you take 2 times this, plus 1 times this, subtract that, you get 0. Right? So it's linearly independent. This one's not. And this one's not either. This vector by itself is linearly independent, but it doesn't span because the only thing in the span of that is multiples of that, right? So you can get any vector that looks like x, 0, but you can't have these two be different, right? So that's the problem here. So it turns out if you want to compute a basis for column space, it turns out that all you got to do is identify the pivot columns. So let's look at an example. We'll figure out both null space, a basis for the null space, and a basis for the column space. So example. Let's look at the following matrix. Let's look at 1 minus 1 minus 2 minus 3. 1 minus 2 is 6. 1 and 2, 1 minus 1, 1. Okay. First, I want to find, let's do the null space first. I'm going to call this A. I want to find null. Okay. What is null A? They are the solutions to the homogeneous problem, right? AX equals 0. We've done this. We've beat this dead horse, and we're going to beat it again. So 1 minus 1 minus 2 minus 3, 11. 3 minus 4, 3, 1 minus 2, 0, 6. and 2 minus 1, no, 2, 1, minus 1, 1. Okay, so let us reduce this, right? This is just like I'm solving AX equal 0. And again, I don't put the augmented ones because they're all zeros. Come minus 3 and add. 1 minus 1 minus 2, 3, 11. Well, minus 3 and add 0. Minus 3 and add is 4. It's going to be 6 minus 2 is 4. 9. That's going to be minus 27. Yeah. And then multiply by minus 2 and add. It's going to be 0. 3. 3. 7. And minus 21. Just because I don't want to multiply by single fractions, I'm gonna do this. I'm gonna take minus 1 times this and add that. So basically, what I'm gonna do, let me kind of mark this out here. I'm going to subtract 3, subtract 3, subtract 7, subtract 21, minus 6. So this is 1 minus 1 minus 2 minus 3, 11, 0, 1, 1, 2, minus 6, 0, 3, 3, 7, minus 1. Right. Okay, so first pivot column done. Second, the second pivot's right here. So I'm going to kill this one, and I'm going to take out what's above and below. So I'm going to just add straight up. And so, well, let me put no below and 1, 1, 1, 2, minus 6. Now, my, just add 1, 0, minus 1, minus 1, 5. And to get down here, I'm going to multiply by minus 3 and add. That's going to be 0, 0, 0, 1 minus 3. Everybody okay with that? And in my final coup de grace, use that 1 to take out what's above it. So this is going to be, bottom row is going to be the same, 0, 0, 0, 1 minus 3. I'm going to multiply this by minus 2 and add up here 0, 1, 1, 0, 0. And I'm going to multiply, I'm just going to straight up add times 1 and add. So that's going to be 1, 0, minus 1, 0, 2. And that's in row reduced echelon form. Correct. So let me write the solution to the homogeneous equation. Let's see, what do we got here? X1, X2, and X4 are basic. And X2 are, I'm sorry, X3 and X5 are free. Everybody okay with that? So my equations are X1 minus X3 plus 2X5 is 0. X2 plus X3 equals 0. And X4 minus 3X5 is 0. And I should be able to get all my variables in terms of, or all my basic variables in terms of 3. So X1 is equal to X3 minus 2X5. X2 is minus X3, and X4 is equal to 3X5. So in vector form, the homogeneous solution looks like x1, x2, x3, x4, x5, which equals x3 minus 2x5. X2 is minus x3. X3 is x3, because after all, that was 3. X4 is 3x5. X5 is x5. So this is x3 times 1 minus 1, 1, 0, 0, plus x5 times minus 2, 0, 0, 3, 1. Well, there's your basis. Null space. Are the vectors 1 minus 1. Well, at least we found this. This is not a unique basis. There are usually many of them. And minus 2, 0, 0, 3. So sometimes we see that's a two-dimensional subspace. Everybody okay with that? Notice that this is a subset of R5, right? It's a two-dimensional subset of R5, right? That's that subset. How are the column space? You know what's really cool? You guys are worried that I'm gonna write that matrix back down again. I'm done, right? This computation will work with column space too. Do you remember the theorem I gave you? That a basis for column of A are the pivot columns of A, right? Okay, so let's look at the matrix that we reduced to. Which are my pivot columns in this is my final product here. Which columns are pivots? Okay, so these are the pivot columns, 1, 2, and 4. I mean, after all, that's how we got our. But those 3 pivot columns are not the basis. Column A. The pivot columns from origin so it should be columns, what was it, 1, 2, and 4 out of this. So it actually should be 1, 3, 2. Minus 1, 1, minus 1, 1, minus 1, and final vector is minus 3. Actually, these could call work well, but I think, but it's only because I'm like, in general, these pivot columns won't work. They're fine for the null space, but they're not good for the column space because we've done row reduction, haven't we, to get those? And that messes up the span of the columns, right? However, linear independence is preserved. Let me point out that the relations are here, right? How can I get, this is not one of the pivot columns. How can I get this from the other 3? Notice that this column right here is -1 times this plus 1 times this. Everybody agree with that? The same thing should happen over here. Look at -1 times this plus this. -1, get -2. -1 plus 1, -2. -1, plus 1 to -1. The relations are all preserved, even though it would be harder to figure out that this thing is 1 times this minus this or whatever, or minus 1 times this plus this, right? It's easy to check from there. The relations are preserved, right? And that's why those pivot columns work, because those 3 pivot columns right here are linearly independent. So the original pivot columns have to be linearly independent, and they span the column space. So be super careful about that. The null space is something you've done before, right? It's basically the vectors you have in the homogeneous solution. For the pivot columns, for the column space, you gotta find the pivot columns, but go back to the original method. Okay. Any questions on that? All right, so your quiz will be up, Friday's quiz will be up soon, and I will see you all by Friday.